Hi there, folks. Today we're looking at congruence in right triangles. We've been looking at congruence in triangles kind of in a general sense, using things like side, 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 or side, angle, side, that kind of stuff. And that still works for right triangles, but right triangles are special, so we'll actually have some more to add to that as we're looking at right triangles. And there's actually one more thing that we can do only with right triangles, because, again, they're special in nature because they're all similar in some way. All right. Remember, a right triangle is just a triangle that has a right angle in it. So right away, all right triangles have one thing in common, and it's that right angle. They always have one congruent angle automatically. Okay. So as we're looking at a right triangle, remember, we've got the right angle. The two sides that create the right angle are called the legs, and the side opposite the right angle is called the hypotenuse. All right. The hypotenuse is always across in the right angle. It's always the longest side of the triangle, that kind of stuff. And those are the things that we're familiar with when we talk about our Pythagorean theorem, okay? So the extra thing that we want to prove here, and once we prove it, once again, we can use it as much as we want, just like when we proved, angle, side, angle, or angle, angle, side, rather. And once we have that, we can use that as a tool to prove triangles are congruent. Same thing here. So hypotenuse leg is kind of the shortcut version that right triangles specifically have, okay? All we need is a hypotenuse and a leg to prove that the triangles are congruent. Now, we don't know that yet. That's what we're going to prove right now. And once we prove this, we'll be able to use that theorem as much as we want. So, given these two triangles are right triangles, and given that AB is congruent to DE, and that BC is congruent to EF, so given that one of the legs is congruent, given that the hypotenuse is congruent, I want to prove that these triangles are congruent. Okay, so given the hypotenuse and the leg, are the two triangles congruent? And once we prove that this is true, we can use this as a huge shortcut for right triangles. Okay, so here we go. Statements and reasons. Everybody's favorite. And there's a couple routes we can take here. Most students, their initial thought is just to start thinking about side, 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 and using the Pythagorean theorem to prove that that third side is correct. And there's a couple things that are problematic with that. One, we haven't technically proven that the Pythagorean theorem is true. We could go through and do that. And here's the thing. We all know that it's true. We've used it for a while. You could go that route. But honestly, that route becomes really, really messy because of going back and forth between congruence and measurements being equal and all the algebra that's involved. It ends up being a very involved proof that way, okay? The other way to do this is to kind of go right to attacking it from the perspective of, can I show this through, something like side, angle, side, or angle, angle, side, that kind of thing, okay? Right now, students will look at this and go, wait, we have angle, side, side. That's not one of our pieces that we can use. Angle, side, side is not a thing. Side, side, angle does not necessarily work, so we can't use that. That's not one of our options, all right? And the problem here is we don't have really anything else to go off of. We have to extend this thing a little bit. So down here, I'm going to extend this guy. I'm just going to draw this out. So I'm going to extend this ray and create a situation where we have something else to work with. I'm actually going to create another triangle here, okay? And so what I'm going to do is I'm going to create a triangle and just put a point out here somewhere in space. And I'm just going to say that I made this guy down here. I called it TD. I'm going to make that congruent to something like AC, okay? So let me start getting some of this written down. I didn't put my given statement yet, so I got to do that. Those are right triangles. AB is congruent to DE. Oh, the tediousness of geometry. Write all these things down. And that was given. Okay? And then the next thing I did is I created a situation. I extended, so I created this ray that kind of extends out. So I constructed, so I'm going to say ray FT with point T, and I created in a way that TD is congruent to AC. Okay? And we can do that. We can copy a segment. That's part of constructions, which I know we didn't do, but we can talk about those things in this format. So I'm just going to say, well, I constructed it that way. Okay, so I constructed ray FT. So TD was congruent to AC. Okay, we just made it that way. All right, anytime we add something to the picture, essentially that's what we're doing. All right, we're just saying, hey, I'm constructing this thing, and we can only construct those basic shapes. Like I can copy a line, that kind of thing. Okay, and so as I kind of look at this thing, I should have used 3 dashes through that. Sorry, so we don't get it confused with the guy with 1 dash. But then from here, like I can copy this angle. We know that's a right angle. And, you know, I could really draw this out and state that that's a right angle, but I'm not going to worry about doing that. We can see that they're right angles. All right angles are congruent. Reasonable justification, we're going to jump right to this. As soon as we see that little box, we can see that these angles right here are congruent. All right, we could add the little steps in there to say, hey, those are right angles because it's given that they're right angles. All right, because that's part of what a right triangle is. And then we could say all right angles are congruent, and then we could move on to the fact that these two triangles, so triangle ABC and triangle DET, well, those are congruent. You can see it by side angle side, okay? So triangle ABC is congruent to triangle DET. And again, I'm just going to go right to saying that's side angle side. I don't want to draw this out too much. Okay? And so as we look at that, if they're congruent by side angle side, it means I can match up this other piece. So like over here, I could match up something like these guys. Okay? So BC and TE, they have to be the same because CPCTC. That was BC. I had to scroll back up to TE. And again, that's because those are corresponding parts. Since I proved the triangles are the same, I can say those parts are the same because of CPCTC. Corresponding parts of congruent triangles are congruent. And so now if I kind of look at the overall triangle that has been created down here with the DEF and DET, if you kind of ignore those two separate triangles and look at triangle TEF, that's an isosceles triangle. We can see it with these two sides being congruent, which means now, can I say that the base angles are congruent? Okay, and I can say that because, well, base angles of isosceles triangles are congruent. So angle, and I'm just going to call it angle T, is congruent to angle F. And yeah, I know technically I shouldn't say angle T there, but there's only one angle we're talking about. I could just label those, put like a little 1 or 2 in there. All right. Sorry, I got to get my justification down. And that's because base angles of an isosceles triangle are congruent. Okay. And now from here, if I look at those two triangles, all right, the two triangles that I'm looking at right now, DET and DEF, all right, I can say that those are congruent because if you look at the pieces here, I have angle, angle, side. And I can think of it as, you know, the angles at D, the angle at F, and then the next line, then DT and the next line, or I could go the other way, but either way, you can see angle, angle followed by a side, so I can say that those two triangles are congruent. So DET and DEF. So triangle DET. Oh, that's a terrible looking congruent sign. I'm ashamed. And triangle, what was it, DEF. And they're congruent because of angle, angle, side. All right. And so now from here, if those are congruent through angle, angle, side, let's think of this in terms of what I already have. I already had that triangle ABC was congruent to triangle DET. And now I have the triangle DET is congruent to triangle DEF. So now I can say that DEF and ABC are congruent, okay? Let me make sure I listed those right, ABC, DEF. And I can say that because of my transitive property. Okay, so the transitive property, I already had, hey, these two triangles are congruent. Now this triangle is congruent to the next one. So now the last two are congruent. Okay, and if you're having trouble seeing that, remember, we said that this guy was congruent to this guy. Then we said that this guy is congruent to this guy. So therefore, the first one's congruent to the last one. That's our transitive property. Okay, and so this is a pretty involved proof, even the way we just did it. All right, if we had done the Pythagorean theorem, it's even worse. Trust me. Okay, trust me, I'm a professional. And so as we're looking at this thing, we now can just use hypotenuse leg whenever we need to. Okay, we don't have to go through all these steps, and this is the kind of the point of why we do these theorem type of things. All right, some of the ones that we've proven in the past, they've been pretty short, and it's only a couple steps. You don't necessarily have to use it every time, but this is one that's really big in terms of cutting out some of the work. Okay, so the theorem says this. If I have the hypotenuse and a leg of one right triangle congruent to the hypotenuse and leg of another right triangle, then the two triangles are congruent. I only need those two pieces, okay? And, part of that hinges on the fact that it's a right triangle, so really it's almost like a side-side angle type situation, but we call it hypotenuse leg because that angle is already assumed, all right? That's part of being a right triangle, okay? So two right triangles, hypotenuse and leg are congruent. The two triangles are congruent. All right, instead of needing three things, I only need two things. So if I look at this particular example, I'm going to apply that to this thing. It says given FCA and EAC are right angles. Let me go ahead and label those before I forget. So FCA is right here. That's a right angle. And EAC, that's a right angle. It also tells me that AF is congruent to CE. All right, so let me label those. And I want to prove that these two triangles are congruent. So here we go. I'm going to start with my statements and reasons. Get those down, get my little column set up. And now I would start off the same way. Once again, I'm just going to write down the given. Okay, and again, that's given. I was told that those things were true. And so now from here, I want to prove the two triangles are congruent. All I need is hypotenuse and a leg because these are right triangles. So I can use that hypotenuse leg. And so as I look at this thing, I have the hypotenuse equal to one another. I have those congruent. I just have to find a leg that's congruent. And once again, it ends up being the thing that they have in common. If we look, AC is a leg of triangle ACE. But AC is also a leg of triangle ACF. And I know that AC has to be congruent to itself. So here I would say that AC is congruent to itself. Once again, that's my reflexive property. That property that we thought we would never use when we first heard about it in algebra. And now from here, if that thing's congruent to itself, that was this guy. Well, if I look at the two right triangles, I have a leg of one match up with the leg of the other. I have the hypotenuse of one match with the hypotenuse of the other. I can immediately go right to saying that the two triangles are congruent. And I can say that because of hypotenuse leg. Okay, that's all I need when I'm trying to prove right triangles are congruent. A hypotenuse and a leg that match up, and I'm done. Okay. If I look at something like this guy, it says find the values of x and y that make the triangles congruent. And so as I look at this thing, once again, if I'm talking about hypotenuse leg, the hypotenuses have to match up. So this guy and this guy have to match up. They have to be congruent, which means they have to be equal. And then the legs have to match up as well. So here, the leg of y and the leg of x plus 2 have to match up. And from here, I just have to solve what I've created, though, is a system of equations, okay? And this is what starts to really get students in terms of geometry sometimes, is as we start to pepper in some of these higher level algebra skills, all right? See, the geometry part of this is easy. Hey, this piece is equal to this piece is equal to this piece, okay? And then whatever the result from that is, we have to deal with it algebraically. And if it's a system of equations, then we solve a system of equations, okay? If it's a quadratic, we solve a quadratic. So this one, I would solve this system by substitution. Right here, y equals the x plus 2. So I'm going to plug that in for y over here. So I replace y with an x plus 2. And now I solve. Here I combine like terms. I'm going to subtract that x. So I've got x equals 7. And now I plug it back in up here. So y equals 9. Okay? These are the values for x and y that I want in order to make these two triangles the same. Okay? If I look at this one, same kind of thing. And just be careful. I have to match up the hypotenuse with the hypotenuse, the leg with the leg. So here, this is my hypotenuse across from the right angle. Here's my hypotenuse across from the right angle. So in other words, 3y equals the 2x plus 4. The legs also have to match up. Here's a leg and here's a leg. So once again, those should be equal to each other. Okay. And so as I look at this thing, probably the easiest way to do this is going to be elimination. And our perception of elimination is kind of funny sometimes. We think we have to have things in a certain way. You've been taught to put this thing kind of in standard form, and neither of these is in standard form at all, but things match up pretty nicely here. If I were to write it like this, y plus 3 equals 2x plus 4. And you could do this one very easily by, sorry, I copied down the wrong thing here. 2x minus 5. You could easily solve that for y and use substitution, but I want to shake things up here, mess with your brains a little bit. And then this guy, 3y equals 2x plus 4. The only thing that really matters in elimination is the fact that you have the variables lined up. And here I have it lined up, even though some of the constant terms are all over the place. It doesn't matter in terms of the format, whether it's standard form or slope-intercept form or whatever kind of format you want, as long as the variables are matched up. And now watch this. I'm going to slap some negative signs on this guy, multiply through by -1. And now I just add them up. See what happens. Here I get a -2y plus 3 equals, over here the x's cancel, and I get a -9. So now I subtract the 3 from each side, that's a -12. I divide by the -2, that's a +6. Okay? And now once I have that y value, I plug it back into either one of these. Maybe I'll plug it in here. So 18 equals a 2x plus 4. I subtract the 4, and I divide by the 2. Just fit it in there. So x equals 7, y equals 6. Okay? And again, you can use substitution or elimination there. It's up to you. All right? I chose to do one of each just to remind you of some of those skills, okay?